Hi, my name is Christiano Gava, and in this presentation I will focus on the main aspects of our paper SphereCraft, a dataset for spherical keypoint detection, matching and camera pose estimation. Data and code are available through the link below. Our dataset is meant to support the development and evaluation of algorithms targeting multiple spherical camera viewpoints. SphereCraft contains over 2 million image pairs for training and testing deep learning models and comprises 21 synthetic and 9 real scenes. We use popular handcrafted and recent learn-based keypoint detectors, namely SIFT, Akaza, Superpoint, and KP2D. It is well known that models and algorithms devised for spherical images must handle the strong geometric distortions present in these images. To address that, we generate images in a wide range of baselines and rotations. More on that in the next slides. Included in all synthetic scenes in SphereCraft are the Blender project, 3D mesh, RGB images, depth maps, and ground truth keypoint correspondences. Also included in SphereCraft but not shown in this slide are the ground truth camera poses and detected keypoints. Here's a summary of what is included. RGB images and detected keypoints, SIFT, Akaza, Superpoint, and KP2D, are available for synthetic and real scenes. However, since the real scenes have neither depth maps nor ground truth camera poses, they are primarily reserved for testing. Synthetic scenes, on the other hand, can be used for training and testing, as depth maps and camera poses are known, which allows the computation of ground truth keypoint correspondences. As mentioned in the previous slide, they also contain the Blender project and 3D mesh. Here we compare our dataset to previous relevant work. SphereCraft is the only existing dataset providing keypoints and their ground truth correspondences. It also offers the highest resolution depth maps. SphereCraft and Replica are the only ones with non-camera poses. While most datasets focus exclusively on indoor or outdoor environments, ours contains indoor, outdoor, and mixed environments. Although Sun 360 also provides both kinds of environments, along with other datasets, it falls into the single image per scene category, meaning it is neither possible to establish keypoint correspondences nor estimate relative camera poses. Consequently, they are not suitable for tasks targeting multiple camera viewpoints. Compared to other datasets, the number of scenes in our dataset is relatively small. However, we point out that out of these scenes, we produce over 2 million image pairs for training and testing, which is much more than can be produced with other existing datasets. To explain how we do that, I need to introduce the concepts of anchor and satellite images. This is the top view of one of our synthetic scenes. Anchor images or anchor cameras are those we manually place throughout the scene. They can be seen as reference images. To understand satellite images, let's take one of the anchors, such as this one shown here, and now for each anchor we randomly generate a set of nearby images within a virtual sphere centered at the anchor camera. Note the different baselines and orientations. This procedure forms a cluster of 10 images, one anchor plus 9 satellites in the current version of our dataset. This process is then repeated for all anchor cameras. This is the resulting cluster for the example above. Note the severe distortions resulting from the different baselines and orientations. At the end, when all clusters are rendered, we have sampled the target scene from several different positions and orientations. We then detect key points on all images and establish correspondences by taking two view combinations of intra and inter-cluster images. For more details on how that is achieved, please refer to section 3.1 in our paper. This yields a vast number of image pairs covering a wide range of baselines and relative orientations, thus generating data for training robust models. As for key point detection, we adopt a divide and conquer strategy by computing a tessellation of the sphere to obtain local planar approximations as shown here. Then, for each local approximation, we create what we call a shard image. A shard image is the projection of the local image defined by the vertices VA, VB, and VC, shown on the left, onto a local tangent plane, but extending this local image by a margin as shown on the right. The purpose of this margin is to provide enough visual context for the computation of key point descriptors, especially those lying near the border of the local image. Key points lying inside the projection of the local face, or the green triangle on the right, are regarded as inliers and mapped back onto the sphere. Inliers are shown in blue here. Those lying outside, the red ones, are regarded as outliers. Note that some outliers will be inliers on neighbor shard images. We repeat this for all key point detectors. Here's a summary of all synthetic scenes in SphereCraft. For each scene, we report its type, the total number of cameras and the number of image pairs, the area in square meters, density, which indicates how dense or sparse a scene is with cameras, and the NDC index we introduce in this paper. NDC stands for Normalized Direct Connectivity. It is computed as the ratio between the average number of neighbor cameras and the total number of cameras. As a result, it encodes size and complexity of the scene. In other words, it infers how challenging a scene is for camera pose estimation algorithms. We suggest this train test split to facilitate the comparison of models and algorithms on our dataset. Here we compare the performance of two learn-based key point matchers: SuperGlue, a state-of-the-art matcher for perspective images, and SphereGlue, developed specifically for spherical images. The goal here is to show the need to develop algorithms and models dedicated to spherical images. Simply applying existing methods originally devised for perspective images to spherical images might work, but are usually clearly outperformed by methods that take the characteristics of spherical images into account, such as strong geometric distortions and a continuity across the left and right image borders. Finally, here are a sample image for each synthetic scene. The number in parentheses indicates the total number of images in that scene. Scenes vary from small and simple to large and complex. And here are the 9 real scenes. We also indicate the resolution of the images in each scene. High resolution images were captured with the Civetta camera, whereas the lower resolution images were captured with the Ricoh Theta S camera. In both cases, the resolution are much higher than those of the synthetic scenes. As for future work, we plan to benchmark different key point detectors, camera pose estimation, and 3D reconstruction approaches on our dataset. It is also possible to add new key point detectors as new approaches are published and code becomes available. We also consider adding spherical optical flow. Thank you for watching this video, and if you have any questions, please do not hesitate to contact me on this email address. I'm looking forward to it.